In a typical ML model evaluation, what we do is we feed a training set, right? And then we train a model, right? So this process creates a model, and the model basically says expresses the output in terms of probability, which is in the range of 0 to 1. And we say if the probability is less than zero point 0.5, predict output as 1, or positive if the probability is less than equal to zero point 0.5, predict output as 0, right? And then what we do is to evaluate how good the model is, we feed it something called a validation set, right? Which is not used in the training example. It is an additional set where we hide the labels. Okay, so this is called an actual output, which that we expect. And then model predicts certain output, right? Then we compare this predicted output with the actual output using a process called evaluation, and we compute various scores such as recall, precision, F1 score, accuracy, and finally area under curve. So these various metrics determine how good the model is. So in this lecture we will go into detail on how to compute these scores. Now one thing to note here is, here we are assuming that the threshold for determining the output is zero point 0.5, but it could change from time to time, and we will see the impact of that on the area under the curve. Okay, so let's take a specific example which will help us drive home the points. So the specific example that we are going to do is, so let's say we have a village in which there are 100 people, okay, and we know that for sure 30 people are infected with virus, right? Now what we want to do is, we don't want to take a chance, and we want to develop an ML model where we can bring in all the people inside a clinic and apply that ML model to predict if the people are uh, infected with virus or not ahead of time, all the people, and we want to see how good the model is. Okay, so let's say the model, we have developed an ML model, and the ML model has predicted that out of 100 people, 40 people are infected with virus. Okay, these are the stats we have. Now let us develop something called a confusion matrix based on this data. A confusion matrix is nothing but it's an information about how good the detection for the ML model is close to the actual uh, cases. So let's say here is the one where we have predicted output. Okay, so predicted output is into two classes: positive, that's the uh, negative, where the people predicted are not infected with the virus; positive, where people are infected with the virus, right? And then we compare this with the actual output, which indicates the actual number of people who are infected with the virus. So negative means the actual number of people who are not infected with the virus, and positive means the actual number of people who are infected with the virus, right? So we know for sure uh, the actual number of people who are infected with the virus are 30. So let's say 20 are here, 10. So this is the actual number of people who are infected with the virus, equal to 30. And our model predicted as 20. So these are the 40 people who our model has predicted with the who have the virus, and the remaining is 50. Okay, let's say this is called confusion matrix, which shows the relationship between the predicted output and the actual output. Now, in a case where the model predicts that uh, a person is not infected with the virus, and that matches with the case where the person is also not infected with the virus, this is called a true negative case. On the other side, the other case is when our predicted output says the person is infected with the virus and it matches with the actual output where the person is also infected with the virus. We have 20 such cases, and these are called true positive. Okay, then cases where our model says the person is infected with the virus, but in reality the person is not infected with the virus, these are called false positive. We have 20 such cases. And in a case where our model says the person is not infected with the virus, but in reality they are, we have 10 such cases, and this is called false negative. Okay, so goal of any ML model is to maximize true negative and true positive and minimize false positive and false negative where there is a mismatch. False positive and false negative indicates there is a mismatch between predicted output and the actual output. True positive and true negative indicates there is a match in the predicted and the actual output. So that means we should maximize it as much as possible. And all metrics that we are going to see, they are nothing but some ratio of this. Using this true positive, true negative, false positive, and false negative. Right? So this is the confusion matrix that's important to understand. Now let's see first metric, which is called the accuracy. So accuracy is nothing but it's a ratio of true positive plus true negative divided by TP, true positive plus true negative plus false positive plus false negative. It basically indicates what percentage of total samples our model has correctly predicted. It could be either positive or a negative. So in this particular case, if you substitute the values, it will be, that comes out to be 70. So 70% is our accuracy, right? So that model is easy to understand. Now let's look at other metrics also. We will look at recall and precision. Okay, so I am drawing that matrix again just for reference. So here is detected, negative, positive, 50, these are TN, 20, these are FP, these are 10, these are FN, and these are 20, these are TP. Okay, and this is actual, negative, positive. So with this reference we saw the accuracy. Now let's see the recall. The recall basically indicates it's a true positive divided by true positive plus false negative It basically indicates what percentage of actual infected people our model has correctly predicted. So if you just substitute the value, so here in this particular case, true positive is 20 plus 10, so this comes out to be 66.67%, right? Then the other model is called precision. Precision is nothing but it's a ratio of true positive divided by true positive plus false positive, and it indicates what percentage of predicted positives that we have are actually infected with the virus. So, right, so we have predicted 40 people in this particular case, which tends to be positive, models predict positive, but how many of them are really positive, truly, actually? That is what precision indicates. So in this particular case, this, if we compute, this happens to be 50%, right? So again, recall and precision, they cause a lot of confusion. So let me repeat it again. Recall indicates what percentage of actually infected people has been correctly predicted. Okay, that is what recall indicates. And precision indicates what percentage of predicted positive are actually infected, right? So there's a very subtle difference, but it's important to understand the difference between precision and recall. Precision indicates whatever you have predicted, how much of that is really true, and recall indicates whatever was actually there, infected people, how many of them you have really correctly predicted. So there's a subtle difference, but very important to understand the recall and precision. Then we want this ratio to be high as well as possible. So F1 score is nothing but 2 into precision into recall divided by precision plus recall. So if you substitute the values, divide by n is equal to 0.4. Okay, so this is the F1 score. One more thing to take into care is the area under the curve, that is often referred as. So area under the curve is nothing but, this is called area under the curve under receiver operating characteristics curve. Okay, so here it's nothing but a graph of false positive rate versus true positive rate, and if you just draw some value, 0.3, 0.4, 0.6 to 1, right? So it's a ratio between TPR and FPR. So true positive rate, again, it's nothing but equal to recall TP divided by TP plus Fn, right? So here in this particular case, plus 10, 20 by 30 equal to 0.67, and false positive rate is equal to Fp divided by Tn plus Fp. So if you calculate this, this will be 0.29. So you calculate TPR and FPR for a given model output and plot one point here. So in this case, let's say our 0.29 and 0.67, that point will be somewhere here, right? Somewhere here, right? So you plot one point for a given model. Then what you do is, in the model that you saw, we predicted our our threshold was 0.5. So we predicted whenever the probability is greater than 0.5, output is 1, else 0, right? And we got these are the number of true positive, true negative, and things like that. Now you can vary the probability threshold to, let's say, 0.6, and recompute TP, FP, TN, and FN, and then you compute TPR and FPR, and you get another point somewhere here. So you keep you keep plotting this points for different thresholds of probability, 0.5, 0.7, 0.9, and you then draw a graph that matches this. Okay. uh, okay, and this graph we want to be as, and you calculate the area under this curve would be, this is the area, right, that we compute, right? So this is the area that we compute for given set of examples for varying value of threshold. A random model will have a curve like this, which is where the TPR and FPR is 0.5, and we want our curve to be above this random model curve, and we want it as we want area to be high as possible. That means the curve should be, so this curve, for example, is better than this curve. This curve is better than of all curves. So the more the curve is leaning to the left, we consider that AUC is better. So these are some of the terms that you should keep in mind while measuring the model, how good the model is. In actual reality, all the scores that we saw, they should be all closer to 1 as possible. Precision, recall, accuracy, F1 score. Our goal is to maximize all of them to 100%. Okay, that should be our goal. In reality, that's often not true. So anything probably that is above 70 to 100, above 70% is often good, and you should always make an effort to improve the accuracy by tuning the hyperparameters of the model or by increasing the training size to make sure the model is as good as possible.